Hello, I'm Ladislav Urban from Dynocortex. We specialize in designing and implementing precision question answering systems using graph databases and AI agents. During work for our clients, we have found repeated patterns where generative AI hallucinations limited the usefulness of otherwise promising applications. When we combine LLMs with GraphRAG, we can use natural language to answer many questions. These solutions were great for certain types of tasks, but their main limitations come when global and local search returns a set of nodes and relations. An LLM tries to generate an answer based on it. The problem comes when the return set is incomplete, too large, and or requires further processing to get the desired answers. One of the main limiting factors of knowledge graphs was understanding schema and creation of queries to extract relevant information. What if we want to answer more complex questions? The other approach is to generate graph database queries based on natural language questions, the schema and topology of the requested nodes and relations. The direct implementation of the mechanism lead to brittle graph database queries and often failures to get the desired results. If we naively generate graph query using LLM to answer complex multi-hop questions, we will get very fragile results. These queries suffer from missing links and inconsistencies of the knowledge graphs. We have found that an agentic approach is able to overcome drawbacks of natural language to graph query transformations. What do we expect from an AI agent? We expect a cost-efficient and fast way to get required results. The return results must be verifiable and explainable. What is the AI agent and what does it do? So it uses a natural language question to find the right answer. It uses knowledge graph as a source of reliable information. It calls LLM templates with various parameters to progress towards the final answer. It forms a workflow with decision points and it can have finite loops. It can call external services to progress in the workflow. Complex workflows are divided into modules, and modules can call other modules to reduce duplication. What techniques are combined in the agentic approach? We use an extraction and reduction of knowledge graph schema based on natural language question. The output is a list of nodes, relations, and properties that are necessary to answer a given question. We also use a selection of examples that are similar to the natural language question and use it as a few shots prompting. The implementation of semantic similarity example selector from LangChain works well for us. We have defined a set of templates of parts of our queries that help LLM to compose multi-hop queries. For example, for queries about variance calculations, we use a reduce S equals 0, rating in ratings, S plus ratings minus average square divided rating count as a rating variance. The agent performs multiple queries to the graph database to get information about nodes and relations of interest. The difference from relational database tables is that each node can have different relations as well as properties, even if it is a node of the same type. We also use iterative process of query generation, validation, correction, and execution. The agent performs assessment of preliminary results to make sure that the results set is not empty or too large. If it's empty or too large, we need to regenerate the query and perform additional computation, summarization, and averaging, and so on. There is also a process of continuous assessment on the set of question query pairs. Now we look at the modules, and one of the important module is knowledge graph queries module. The goal of this module is to take a user question and form a graph database query to get required records. It is composed of 4 parts and depends on calls to other services. It does have its own internal workflow. We are trying to generate a cipher query that is aligned in the same time with user question, cipher syntax, schema or its subset of the graph database, and existing, often incomplete relations and attributes in the graph database. The submodule generator. Generator takes as an input user question, examples of similar questions, and matching cipher code of similar questions, and subset of graph database schema to formulate a cipher query via calls to LLM. It uses a semantic similarity example selector to return an optimal number of examples for a few-shot prompting. We need to keep in mind that even a correct cipher query might not get the required results because of missing attributes and relations in the graph database. There are often many possible cipher queries that can return required data. If we get multiple different cipher queries that use different paths to return the same answer, we do have a high confidence of correctness of the answer. This means that we have found more evidence to corroborate the given answer. The submodule validator. Validator uses tools to validate cipher syntax. One of them is a call to explain cipher statements to get syntax and mapping issues. The second one is to call LLM to elaborate on the issues found by the call to explain syntax. The output from this module is a list of issues that need to be corrected in order to create a valid cipher statement to answer the user question. A submodule corrector. Corrector uses programmatic means of correcting cipher syntax as well as calls to LLM. We do have corrections of direction of relationships between nodes and correction of properties of nodes. Other types of corrections include recognition of name entities in the graph database. The entities in the user query can be called by alternative names, identified by previous context or by description. The executor submodule. Executor is responsible for handling cipher query execution on a graph database, as well as returning back result, structural information, errors, and missing links, nodes, and attributes. The module schema filter. It reads the full schema of the graph database, and that can be quite large. It uses the full schema and natural language question to ask LLM to return all relevant node types. It runs a graph database query to return all possible relationships and properties types of given node types. This, together with the node type names, is our reduced schema. Final decision module is a scorer submodule. It determines that a given set of knowledge graph results that includes metadata indeed answers the original user question. Then there is a name entity submodule. It is used at several places to find actual named entities mentioned in the user question or found by queries. It calls an LLM template with input parameters such as user question and filtered node types to generate cipher code to find and read full content of all name entities from the natural language question. It tries to execute the generated cipher code, and in case of syntax error, it runs LLM corrector to correct the syntax. It executes the cipher code to get the relationships and properties from the nodes and store the results. We plan to release Dynocortex agent as an open source in a few months. Please do not hesitate to comment and give us suggestions. That is all for today, and thank you for your attention.